Concept 40.2 is all about homeostasis, the word homeostasis. Feedback control maintains the internal environment in many animals. For a creature to survive and live, especially a complex creature made up of trillions of cells, you have to deal with the ever-changing external environment, and the ups and downs that the external environment goes through is not really good for life. So one day you have plenty of food, the next day you have none. One day it's hot, the next day it's cold. One day you have plenty of water, the next day you have none. So a living creature has to deal with that and somehow still maintain a fairly stable internal state. So we're going to talk about how living creatures do that through various feedback control mechanisms. Animals manage their internal environment by regulating or conforming to the external environment. Sometimes they will match the outer environment, sometimes their body will work against the outer environment, whatever it takes to maintain stability on the internal side of the equation. So we're going to talk about either a regulator or a conformer. A regulator uses internal control mechanisms to moderate internal change in the face of external conditions. So a regulator is going to look at the fluctuations in the outside world and say, no, we're not going to go with that. We're going to try to keep things steady on the inside through a variety of mechanisms. A conformer is the opposite of that. A conformer will take the changes going on in the environment and, at least to some degree, allow those changes to affect its internal condition. So a conformer will allow its internal conditions to vary, at least somewhat, not always to the extremes, but somewhat with the external environment. And animals may regulate some environmental variables while conforming to others. So you wouldn't say, well, a lizard is a conformer and a mammal is a regulator. It's not quite that overall, it's not a blanket statement. All creatures, to some degree, tend to be both of these. In some cases they will be a regulator and their body works against whatever the outside environment is. In other cases they might be a conformer and their body changes with the external environment. A good example used in your book is with body temperature and environmental temperature. If you're looking at a mammal like a river otter, you'll notice as he is a temperature regulator. You'll notice that his change over time is not much affected by the ambient environmental temperature. So down at the bottom here we have the ambient environmental temperature. As it goes up, say from 0 to 40, you see the river otter's temperature tends to stay very much the same. Compare that to a largemouth bass who is a temperature conformer. He, for the most part, will adjust his internal temperature, or it's more based on the external temperature. So as the external temperature goes up, you can see his internal temperature goes up. And that's just a great example of either a conformer or a regulator. The word we're looking at is homeostasis. Homeostasis means steady state, and that's what creatures are trying to do to some degree, is achieve a steady state or internal balance regardless of what's happening on the outside. In humans, say, good examples of things the body has to regulate would be body temperature, blood pH, glucose concentration within the body. All of these need to be maintained at a fairly constant level. There is not a lot of variance that can take place. So you have a narrow range that they can fall in. They can go up and down a little bit, but you start to go outside of the range and you're going to have to deal with that. You're going to start to have some problems. So imagine if your body temperature wasn't well regulated. Imagine if every time you drank a cup of coffee, your body temperature soared because you ingested the hotter liquid material. Or on a cold day, the moment you stepped outside, your body temperature starts to plunge because it's 25 degrees outside. Well, our bodies work hard to keep that from happening. That whole process is called homeostasis. When you think about homeostasis in living creatures, you need to think of an example of, say, a non-living system that works the same way. And a room thermostat, say in the classroom or in your house, is a perfect example. The room thermostat has a set point. Let's say it's winter and you've got the thermostat set at 70 degrees. So the external temperature drops down to 30, and that starts to cause the internal temperature of the house to drop lower and lower. Well, you might have the set point of the thermostat at 70 degrees, and when that temperature drops below that set point, that serves as a stimulus, which causes a response of some kind. You have a sensor that detects this change. In this case, we're talking about the thermostat, the internal part of the thermostat. That detects the change, causes a stimulus, which triggers a response. In this case, it would be turning on the heater. So the thermostat says, whoa, we're dropping below our set point. So the response is to kick on the heater. The furnace comes on, blows warm air, and raises the temperature. The response returns that variable back to the set point, or perhaps even a little bit above that set point and tries to keep it right there. So you have this feedback mechanism, and the same thing, it works the same way in biology, where here you have the set point, which is the room temperature. When it falls below that, you cause a response. When it's at that point, you shut off the response. So think about a room thermostat controlling room temperature. It works the same way, although perhaps a bit more complicated in biology. There's two different methods of feedback when we're talking about homeostasis. We have what we call negative feedback and positive feedback. For the most part, homeostasis is maintained by what we would call negative feedback, which helps return a variable back to the normal range or the preferred range. What this means is that in the control system of negative feedback, the buildup of the end product shuts the system off. So for example, your thermostat in the house works off of negative feedback. Once it drops below 70 degrees, it kicks on the heater. Once the heat rises to a certain level above 70, that causes the system to shut off. So once you get enough of what you need, that shuts down the process. That's negative feedback. The opposite of that would be positive feedback, and positive feedback is seen less in biology concerning homeostasis, but it is sometimes used to drive a process to completion. And a good example is the contractions that occur in childbirth. Those muscular contractions start a process of positive feedback to where the contractions get stronger and stronger and faster until childbirth is complete. Or the clotting process, the chemical blood clotting process, when you get a cut or you scrape open the skin, there's a clotting process that once it starts, chemicals are released that further and enhance that and speed up that process, and that's positive feedback. So negative feedback would be, okay, you have something you need. When you get enough of it, you shut off the system. Positive feedback means I want what I'm getting and I want more and more and more of it, and it speeds up and increases the process until finally it reaches its fruition or its completion point. If you think about negative feedback, I like to think of it as a guy on a teeter-totter. If I were to set a book on this end of the teeter-totter, it would start to tilt him down this direction to the left, and he would compensate by leaning right to keep himself steady. That's negative feedback. It's like, okay, I see what we've got here, and I'm trying to avoid that. I'm trying to avoid more of that. Or I'm trying to keep that from happening more. That would be negative feedback. So like with the heater in your room, once you get the heat that you need, the thermostat says, oh, okay, well, I don't want any more of that. I've got all that I need, so it shuts off the heater. In this case, he says, I want to maintain level, so that extra weight, he's going to compensate by leaning to the right to keep it level. If we're talking about positive feedback, that would be we want a process to start, we want it to continue. So positive feedback would be you set the book on the left, and he wants the end of the teeter-totter to hit the ground. So he will join in with that process and start to lean left, and then the teeter-totter will tilt more and more and more until it hits the ground. That's positive. We want it to continue. We want more of it until we reach a certain point. So negative feedback shuts it off when you get enough. Positive feedback just keeps on adding on until you finally get to the point of completion. There are a couple of good animations here. They should be in the notes folder, or you can, if you're watching the PowerPoint, you can right click and hit play. Here's negative feedback, which is most common in homeostasis, and then here is one for positive feedback, which is less common in maintaining balance in homeostasis, but is still present in some particular instances. When we talk about maintaining this balance, this homeostasis, you have to remember that this is not always a single set point that never changes. Some of these ranges or set points can change over time. They can change with age. For example, you have a pretty radical shift in hormone balances that occur in puberty, or they sometimes show what we call cyclic variation, like they change with the seasons or they change with the day and night. In animals and plants, we call this a circadian rhythm, and the circadian rhythm kind of governs the physiological changes that occur in their body pretty much on a 24-hour cycle of day and night. So you can actually see that in body temperature, melatonin concentration. You can measure the body temperature of a human being over a 24-hour period, and you'll see changes that pretty much correspond with a kind of a 24-hour cycle of light and dark, night and day. Same thing with the melatonin concentration, a chemical within the brain. You'll see a circadian rhythm that occurs throughout this 24-hour period. Homeostasis can also adjust over time to changes in the external environment. This is a process called acclimatization. You're becoming acclimated to a particular environment. So, for example, if you were to move from Florida down by the seashore and you were to move to Colorado, and you move to Denver, Colorado, which is over 5,000 feet up into the air, you're going to have much thinner air in Colorado with less oxygen. And it's going to take a while for your body to become acclimated. There's going to be physical changes that occur in your body so that you can learn to live at that higher elevation and you become acclimated to that process. So that's going to change the set point. That's going to change the balance point within your body over time. Now you want to keep in mind this is not what we would consider adaptation or evolution. Here what we're talking about is a temporary change that occurs during the animal's lifetime. So for example, elk, as the seasons change, they move up and down the mountainside. During the winter, they'll be low down in the valley, and maybe during the summer, they'll move higher up into the mountains. Well, as they move higher into that higher altitude with thinner air, it's going to take a while for their body to become acclimated. And there are certain physical and physiological changes that occur inside their body relating to respiration and blood pH and that type of thing. But again, becoming acclimated, or this acclimatization, is not the same as adaptation. So becoming acclimated is a temporary change that happens during your lifetime. Adaptation and evolution is a process of change in a population brought about by natural selection over many generations and long periods of time. So we're going to take a break right there. That's the basics of homeostasis. We're going to look at one particular example. We're going to talk about body temperature regulation. That's going to be our good example. That'll be concept 40.3. So let's take a break. We'll come right back.